fundamental force is a basic mechanism of interaction between one particle with another particle, which the interaction can no longer be explained by other basic interactions. In our universe there are four fundamental forces, namely the strong nuclear force, the electromagnetic force, weak nuclear force, and gravitational force. If even one of these four fundamental forces did not exist, the universe would not exist. The mention of this fundamental force is often referred to as the fundamental interaction. So the words style and interaction are often used interchangeably. The four basic interactions are often described according to their relative strength. Gravity is considered to be the weakest interaction in the universe, followed by weak interactions, electromagnetic interactions to the strongest interactions, namely strong nuclear interactions. If the magnitude of the value of the strong force is 1, then the magnitude of the electromagnetic force is a 137th. Then the weak force is 10 to the power of -6 and gravity is 6 times 10 to the power of -39. The gravitational force and the electromagnetic force are two interactions that have been known long before the discovery of strong nuclear interactions and weak nuclear interactions. This is because the influence of the two interactions forces on the normal objects are easily observed by humans. The new strong and weak interactions were discovered by scientists in 20th century when scientists began to investigate and research about the atomic nucleus. Gravity was originally described systematically by Sir Isaac Newton in the 17th century as a force or force that acts on all types of objects that have mass. Gravity causes apples to fall from trees and determines orbit planets around the sun. However, Newton's law of gravity has not been able to explain how gravity works. This can only be explained by Einstein in his general theory of relativity. In the general theory of relativity, gravity, previously thought of as the interaction of distances between objects at a distance, replaced by the concept of curvature of spacetime. In a study of particle physics or in some candidate theories of quantum gravity, for example string theory, gravity is believed to be mediated by hypothetical, force-carrying particles called gravitons. Called a hypothetical particle because of the physical presence of the graviton has not been proven experimentally. Gravity is an interaction with an infinite range of distances. The magnitude of the gravitational force will decrease with increasing distance but will never be zero. Electromagnetic interaction, whose scientific definition was first given by James Clerk Maxwell in the 19th century, responsible for the repulsion of similar electric charge and the force of attraction of different types of electric charges. The greater the charge, the greater the interaction. As the name suggests, the electromagnetic force consists basically of two parts, that is, electric force and magnetic force. More specifically, the electromagnetic force is manifested by the force between electric charge, Coulomb's law, and magnetic force. Both are summarized in Lorenz's law of force. Electromagnetic force is a force with infinite distance which obeys the law of inverse square and has the same shape as gravity. The electromagnetic force works by being mediated by a boson gauge. A boson gauge is a type of elementary particle that will respond to communicate a certain force. In the case of the electromagnetic force, the boson gauge in question is a photon particle. When an electron enters the interaction area, it will emit a photon, and the photon will propagate to another electron. Then communicates the electromagnetic force, then vanishes. Through this photon exchange, photons mediate a force and convey information from one place to another. Weak force, or also called weak core interaction, is responsibly in particle decay. Physicists describe this interaction through the exchange of particless force carriers called the W and Z bosons, weak bosons. When subatomic particles such as protons, neutrons and electrons are in a distance of 10 to the -18 meters, equivalent to 0.1% of the proton diameter from each other, then the particles will exchange this type of boson W and Z bosons. As a result, subatomic particles decay into new particles. The weak force is very important for the nuclear fusion reactions that occur in the nucleus of the Sun, which then produces the energy needed for most life on Earth. Because of the weak force, archaeologists can use carbon-14 to determine the age of an artifact or fossil. Carbon-14 has 6 protons and 8 neutrons. One of those neutrons decays into protons to make nitrogen-14, which has 7 protons and 7 neutrons. This decay occurs at a predictable rate, so that allows scientists to determine how old the artifact is. The strong force acts between the quarks, the elementary particles that make up all subatomic particles, including protons and neutrons. The strong force holds quarks together to form protons and neutrons. The strong force only works when the subatomic particles are very close to each other. The subatomic particles in question must be within 10 to the power of -15 meters from each other, roughly the length of a proton's diameter. Unlike other fundamental interactions, the magnitude of the strong force will becomes weaker as the subatomic particles move closer together, so the strong force will reach its maximum value at the farthest range along the proton diameter and will weaken if the distance is shortened. Once within range of a massless charged boson called a gluon, transmit or exchange strong forces between quarks and make the quarks glued together. So, how do you understand the four fundamental forces? Without these four forces, the universe would never exist. Hopefully this video can give you insight into possible laws of nature. You missed the first physics lesson. Like if you like this video, comment if you have any questions, and don't forget to subscribe.